Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine taking 150 Earths.
That is a staggering amount of material.
Right. Just picture every single ocean, every mountain range, every sprawling continent, and, every molten iron core.
Just an incomprehensible volume of solid rock and metal.
Exactly. Now, I want you to take all of that solid mass, grind it down into cosmic dust, and dissolve it entirely into the atmosphere of a single raging gas storm.
A storm that is spinning something like 1.5 billion miles away from its sun.
Yeah, 1.5 billion miles. By every established metric of planetary physics, an object like that shouldn't be mathematically possible.
It really shouldn't. I mean, the mechanisms required to build something that massive, that far out in the frozen reaches of a star system, they just don't fit into our standard models.
Right, our models of how the universe is supposed to work. But today, we are looking directly at a celestial behemoth that did exactly that.
It's an object that basically forces us to question the fundamental dividing line between planets and stars.
It totally blurs that line.
It forces a complete reevaluation, yeah. Because, well, we find deep comfort in neat categorizations.
Well, it's absolutely human nature, right? We love our little boxes.
We really do. We prefer a universe where you have, planets on one side, objects built from rock and ice that maybe sweep up some gas over time.
And then stars on the other side.
Exactly. Stars being these massive, self-collapsing clouds of nuclear fire. We like a hard, absolute boundary there.
But when you actually examine the extreme edges of astrophysics, that boundary doesn't just blur. It it completely dissolves.
It does. You find objects that possess the defining characteristics of both, existing in this state of absolute diagnostic contradiction.
And that brings us to the specific anomaly you asked us to investigate today. We're talking about 29 Cygni b.
The ultimate cosmic gray area.
Yeah. And just to anchor the scale here for you, 29 Cygni b is a gas giant with a mass roughly 15 times that of Jupiter.
Which is just a terrifying amount of mass.
15 Jupiters mashed together into a single sphere. And it maintains an orbit at a staggering distance of 1.5 billion miles.
That's about 2.4 billion kilometers for anyone doing the conversion.
Right. So if you drop this system into our own solar neighborhood, 29 Cygni b would be orbiting at almost the exact same distance Uranus is from our sun.
Which is precisely the detail that makes this such a profound mystery.
Because it's so far out in the dark.
Exactly. You have a mass that borders on the stellar, right? But combined with an orbital distance that sits in the deep freeze of a planetary system.
Well, it's basically having an identity crisis.
A massive one. When you look at the mechanics of how celestial bodies are actually constructed, 29 Cygni b challenges the timelines, the material availability, and just the fundamental physics of the whole construction process.
So our mission for today is to figure out how astronomers unraveled that identity crisis.
It's a fantastic piece of detective work.
It really is. We need to look at how a team led by William Ballmer at Johns Hopkins University and the Space Telescope Science Institute actually managed to prove something incredible.
Right, that even the most massively incomprehensible gas giants can be built from the ground up.
Even the ones we'd traditionally suspect of being, like failed stars. But before we get to the detective work with the James Webb Telescope, we need to lay down some ground rules.
We have to understand the baseline, yeah.
Right. We need to understand the two very distinct, fundamentally opposed ways the universe goes about building worlds.
Because the universe essentially operates two completely different construction sites.
Okay, let's look at the first one. This is the process that built the ground we are sitting on right now, right?
Yes, the bottom-up process. It's traditionally known as core accretion. This is the classic, standard mechanism for planet formation.
Okay, let's break down accretion, because it sounds simple on the surface, just stuff bumping into other stuff.
Like rolling a snowball.
Right. But the physical reality of doing that on a cosmic scale has to be intensely complicated.
Oh, it is incredibly complex.
Yeah.
And it operates under a strict, unforgiving time limit.
Wait, a time limit? Why?
Well, core accretion begins inside a protoplanetary disk. When a newborn star ignites, it doesn't consume all the material in its stellar nursery.
So there's leftovers.
Exactly. The star is surrounded by this vast, flattened, spinning disk of leftover hydrogen, helium, and a tiny, tiny fraction of microscopic dust grains.
How microscopic are we talking?
Unimaginably small, often just fractions of a micron across. They're mostly composed of silicates, carbon, and ice.
So the star is sitting in the center of this spinning cosmic soup. But how do those microscopic grains ever become something the size of Earth, let alone Jupiter?
It takes a lot of steps.
Because gravity can't possibly be strong enough to pull microscopic dust together, right?
You're absolutely right, it isn't. In the very early stages, gravity is entirely irrelevant. The initial growth relies entirely on electrostatic forces and molecular bonds.
So it's basically just chemistry at that point.
It is quite literal chemistry. As these microscopic grains drift through the gas in the disk, they collide. And if the collision is gentle enough, van der Waals forces.
Those are the slight electromagnetic interactions between molecules, right?
Yeah, exactly. Those forces allow them to stick together. They form these incredibly fragile, fluffy aggregates. Think of like cosmic dust bunnies.
Okay, dust bunnies I can visualize.
But as they grow to the size of sand grains and then pebbles, they face a gauntlet of physical challenges.
Challenges like what? I mean, I assume space is mostly empty, so shouldn't they just keep coasting and sticking together?
You have to remember the disk is mostly gas, and that gas creates aerodynamic drag.
Oh, so they're fighting a headwind.
Exactly. As these pebbles grow larger, they begin to decouple from the gas flow. They experience a serious headwind. This headwind saps their orbital momentum, which causes them to slowly spiral inward toward the star.
So they're falling in. That seems like a bad design.
It gets worse. Once objects reach about the size of a boulder, roughly a meter across, the electrostatic forces are no longer sufficient to hold them together if they collide at high speeds.
So instead of sticking,
They shatter. They smash each other back into dust. This is famously known in astrophysics as the meter-size barrier.
that sounds like a fundamental flaw in the planetary assembly line. If boulders just smash each other back into dust or spiral into the star because of gas drag, how does anything ever survive long enough to become a planet?
That was a persistent headache for astrophysicists for decades, actually.
I can imagine. So what's the workaround?
The current understanding involves areas of the disk where gas pressure is slightly higher, creating local traps.
Like pressure pockets.
Yeah, pressure bumps. In these bumps, the gas headwind essentially disappears, allowing the pebbles and boulders to accumulate in massive, dense swarms.
Also a cosmic traffic jam.
A perfect analogy. And when the density of these solid swarms reaches a critical threshold, their collective mutual gravity finally takes over.
So gravity finally kicks in.
Big time. The entire swarm collapses in on itself almost instantly, completely bypassing that meter-sized barrier to form solid bodies that are hundreds of kilometers across.
And those are the planetesimals?
We call them planetesimals, yes.
So chemistry gets you to pebbles. Aerodynamics forces the pebbles into dense traffic jams, and then gravity suddenly forces the traffic jam to collapse into a solid rock. That is the core in core accretion.
Precisely. And once you have a planetesimal, gravity rules. It sweeps through the disk, using its gravitational cross-section to pull in surrounding pebbles and other planetesimals.
So it just bullies everything else in its path.
It really does. It
Wow.
grows into a protoplanet. Now, if we are talking about building a rocky world like Earth, the process largely stops here. That takes tens of millions of years.
Okay, but what if we want to build a Jupiter?
If we are building a gas giant, the protoplanet must reach a critical mass, typically around 10 times the mass of the Earth, very, very quickly.
Why the rush, and why specifically 10 Earth masses?
10 Earth masses is roughly the threshold where the solid core's gravity becomes so intense that it can begin to hold on to the surrounding hydrogen and helium gas.
Oh, against the thermal pressure trying to push that gas away.
Exactly. At first, it is a slow bleed. The core pulls in a thin envelope of gas. But as that envelope cools and compresses, it allows more gas to fall in.
It's snowballing.
It leads to a dramatic tipping point. Once the mass of the gas envelope equals the mass of the solid core, the planet undergoes runaway gas accretion.
A runaway accretion, so it just violently vacuums up the rest of the gas.
Violently and rapidly. It vacuums up astronomical volumes of gas, swelling into a Jupiter-sized giant in a fraction of the time it took to build the actual core.
Okay, but earlier you mentioned an unforgiving time limit. Where does the ticking clock come into play during this runaway accretion phase?
The clock is dictated by the host star itself. You see, a newborn star is wildly active. It emits fierce ultraviolet and X-ray radiation, along with these really powerful stellar winds.
So it's blasting the disk.
Constantly. These high-energy photons bombard the surface of the protoplanetary disk, superheating the gas. And as the gas heats up, its thermal velocity increases.
It gets too hot to hold on to.
Eventually, yes. The gas molecules are moving so fast that they exceed the gravitational escape velocity of the entire star system.
They just boil away into deep space.
They do. This process is called photoevaporation, and it will completely strip a typical system of its gas within roughly 3 to 10 million years.
Wow. 3 to 10 million years on a cosmic scale is like nothing.
It's the blink of an eye. And once the gas is gone, the runaway accretion process is dead. If a solid core hasn't reached that 10 Earth mass threshold by the time the gas evaporates, it will forever remain a rocky or icy world.
So that's why we have so many rocky worlds and so few gas giants.
Exactly. Building a giant requires threading an incredibly tight needle. You have to navigate the meter-sized barrier, build a massive core, and trigger runaway accretion before the star blows all the raw materials into the void.
Okay, that paints a remarkably chaotic and difficult picture of bottom-up planet formation. It is a wildly inefficient process.
Highly inefficient.
Let's pivot to the second recipe then. Because if accretion is a desperate race against the clock, the top-down process fragmentation feels like an entirely different category of physics.
It is entirely different, both in mechanism and in scale. While core accretion happens inside the disk around a star, fragmentation is typically the mechanism that forms the stars themselves.
So we're talking about a much larger scale here.
Massive. We're talking about events that occur inside giant molecular clouds. These are unimaginably vast structures of cold, diffuse gas drifting in the interstellar medium.
Like how big?
Oh, often spanning dozens of light years across.
Okay, I am struggling to visualize how something that vast and diffuse turns into a dense, burning star. What actually initiates the collapse?
It all comes down to a battle between thermal pressure and gravity.
Heat versus weight.
Exactly. Even though the gas in a molecular cloud is incredibly cold, often just a few degrees above absolute zero, the molecule still possess thermal motion.
Right, they're still vibrating.
They vibrate and bounce off each other, creating an outward pressure that keeps the cloud inflated. However, these clouds are not perfectly uniform.
They have lumpy bits.
They have slightly denser pockets, yes, perhaps triggered by a passing shock wave from a distant supernova or even the galactic magnetic field.
So gravity is trying to pull the pocket inward, while the heat of the gas is trying to push it outward.
You've got it. And there's a mathematical tipping point for this, known as the Jeans mass, named after the British physicist James Jeans.
The Jeans mass, okay.
The Jeans mass dictates that if a clump of gas reaches a certain critical density and is cold enough, the outward thermal pressure simply cannot support the inward pull of its own gravity.
And when that happened?
The moment that threshold is crossed, the entire clump becomes gravitationally unstable. It enters a state of free fall.
A sudden, violent collapse. So not millions of years of gathering pebbles, but an instant structural failure of the cloud itself.
The scale and speed are just orders of magnitude different from accretion. As the pocket collapses, the material compresses, increasing the density.
Which only accelerates the gravity.
Exactly. The center of this collapsing fragment grows incredibly hot and dense, eventually igniting nuclear fusion and becoming a star.
And the leftovers form the disk.
Right. The remaining gas swirling around it flattens out into the protoplanetary disk we just discussed.
Okay, but this creates a major logical hurdle for me. You just described the process for making a star. A massive nuclear fusing furnace.
I did.
But the object we are investigating today, 29 Cygni b, is definitively categorized as a planet. Why are astronomers even applying star formation physics to an object that orbits a star?
And that is the core of the diagnostic muddy waters we find ourselves in today, because, as it turns out, the universe doesn't restrict fragmentation solely to stellar nurseries.
Wait, really? Where else does it happen?
Under very specific conditions, it is theoretically possible for a localized version of fragmentation to occur within the outer, tenuous edges of a protoplanetary disk itself.
Inside the disk.
Astronomers call this disk instability, or top-down disk fragmentation.
So you have the star already formed, you have the disk spinning around it, and instead of pebbles slowly gathering to make a planet, a massive chunk of the disk just suddenly collapses.
Conceptually, yes. Imagine the outer fringes of a massive, early-stage protoplanetary disk. We're talking perhaps 1 billion miles or more away from the central star.
Out where it's incredibly cold.
Exactly. Out there, the radiation from the star is incredibly weak. The gas in the disk is profoundly cold, which means its outward thermal pressure is very, very low.
So it's vulnerable to gravity.
Highly vulnerable. If the disk is massive enough, The sheer weight of the gas can trigger a localized gravitational instability. A large spiral arm or clump within the disk can suddenly fragment and collapse in on itself.
Wow. And how long does that take?
It forms a massive gaseous body in a matter of hundreds or thousands of years.
Oh, wow, rather than millions.
Exactly. It skips the rock gathering phase entirely. It just takes a massive bite out of the gas disk all at once.
And because it forms so quickly, it completely bypasses the ticking clock of the star evaporating the disk.
Precisely. Disk fragmentation is the leading theoretical explanation for why we occasionally find incredibly massive gas giant-like objects orbiting at extreme distances from their host stars.
Which brings us directly to the paradox of 29 Cygni b, because this object seems mathematically designed to frustrate both of these theories simultaneously.
It is the perfect troublemaker.
Let's look at the numbers. Lead researcher William Ballmer and his team at Johns Hopkins zeroed in on 29 Cygni b because it sits at roughly 15 times the mass of Jupiter.
Right.
Now, I know that in the context of our solar system, 15 Jupiters is terrifyingly huge. But in the context of these two formation models, why is that specific mass such a massive headache?
Because 15 Jupiter masses represents the fulcrum point between the absolute limits of both theories.
It's right on the boundary.
It is a mass that should theoretically be impossible for either mechanism to comfortably achieve.
Okay, let's start with the top-down fragmentation model. Why is 15 Jupiters a problem there?
Well, when a cloud of gas collapses, whether it's in a molecular cloud or a disk, it creates a massive gravitational well. It naturally wants to gorge on the surrounding material.
It's greedy.
Very greedy. It wants to become a star or at least a brown dwarf, a substellar object massive enough to fuse deuterium, but not standard hydrogen.
So a collapsing cloud doesn't just stop halfway, it pulls in everything it can reach.
Exactly. The physical mechanics of fragmentation naturally produce massive objects. In hydrodynamic computer simulations, trying to get a fragmentation collapse to halt its growth at merely 15 Jupiter masses is incredibly difficult.
It wants to keep growing.
There is an opacity limit in the physics of collapsing gas that makes forming small fragments extremely inefficient. 15 Jupiter masses is essentially the absolute floor. It's the lowest possible mass you could realistically expect a top-down collapse to produce.
It's the smallest possible star-like collapse. Okay, but what about the bottom-up accretion side? If it's the floor for fragmentation, how does it fit into the pebble-gathering model?
It acts as the absolute ceiling.
The ceiling.
Yes. We established that core accretion is a race against time. To build a core, trigger runaway gas accretion, and swallow 15 Jupiters worth of mass before the star's radiation boils the disk away, it basically stretches the timeline of physical models to their breaking point.
The math just doesn't work out.
Achieving 15 Jupiter masses through accretion requires a disk of unimaginable density, perfect conditions, and zero interruptions. It is the absolute highest mass a bottom-up process could plausibly yield.
I see the dilemma. You have an object sitting exactly on the razor's edge. It's either the smallest possible fragment or the largest possible accretor.
Stubbornly right in the middle.
But I want to push back on the accretion theory here, because we haven't factored in the orbital distance yet. 29 Cygni b is 1.5 billion miles away from its host star.
Which is immense.
Out at the distance of Uranus, the available material in a disk is incredibly sparse. Right? The dust and pebbles are spread over a massive volume of space.
They are very thinly distributed.
And orbital velocities are sluggish out there, meaning planetesimals aren't exactly sweeping through material very quickly. Doesn't that sheer distance almost entirely disqualify the slow bottom-up process?
Your intuition is aligned perfectly with the historical assumption of the astronomical community.
So they thought the same thing.
They did. The standard model of core accretion dictates that building a 10 Earth mass core at a distance of 1.5 billion miles should take tens, perhaps hundreds of millions of years.
But the gas in the disk evaporates in under 10 million.
Exactly. The math simply does not close. Therefore, the long-standing assumption has been that any massive object found at those extreme distances must be the result of sudden top-down disk fragmentation.
Because bottom-up accretion shouldn't be physically capable of operating fast enough in that sparse, frozen environment.
That was the accepted logic, yes.
But the Ballmer team wasn't satisfied with a logical assumption. They didn't want to just guess that it was fragmentation based on the distance.
Well, they wanted proof.
They wanted definitive physical proof of how 29 Cygni b was constructed. And to get that proof, they couldn't just rely on math. They needed to actually look at the object. They needed to analyze its structural DNA.
Which is an undertaking of monumental difficulty.
I can imagine.
I mean, you are attempting to isolate the light of a planet located billions of miles away from us, sitting immediately adjacent to a star that is millions of times brighter than the planet itself.
This is where the James Webb Space Telescope enters the narrative.
The perfect tool for the job.
Because standard ground-based telescopes, and even the Hubble Space Telescope, they don't have the specific capabilities required to pull this off. Balmer's team had to use one of the most advanced instruments on Webb, the near-infrared camera, or NIRCam.
Yes, NIRCam.
But they couldn't just point and shoot. They had to utilize a very specific optical technique called coronagraphy.
A vital technique.
Now, as we know, directly imaging an exoplanet is often compared to trying to spot a single firefly hovering right next to an industrial searchlight from miles away.
It's an excellent comparison.
So how does a coronagraph actually solve that contrast problem?
It is a brilliant piece of optical engineering. When light from a distant star enters a telescope, it doesn't just form a single perfect point on the detector.
It spreads out.
Right. Due to the wave nature of light, it diffracts around the edges of the telescope's mirrors. This creates a bright central point surrounded by a series of concentric rings of light known as an airy pattern.
Okay.
Even if the planet is physically separated from the star, the glare from those diffraction wings will completely wash out the faint light of the planet.
So the star is essentially bleeding light across the entire image.
Exactly. A coronagraph is a complex series of masks and optical baffles housed inside the NIRCam instrument itself.
So it's hardware, not just software.
Physical hardware. The first mask physically blocks the central brightest core of the star's light.
Like putting your thumb up to block the sun.
Exactly like that. But that doesn't solve the diffraction rings. So the light passes through further optical elements, specifically something called a Lyot stop.
A Lyot stop. What does that do?
The Lyot stop is meticulously designed to match the specific geometry of the telescope's primary mirror. It actively suppresses those scatter diffraction rings, essentially creating an artificial, near-perfect eclipse inside the camera.
That is wild.
By carefully managing how the light waves interfere with themselves, the coronagraph dims the star's glare by factors of tens of thousands, completely revealing the space immediately surrounding it.
It's an internal engineered eclipse.
Exactly.
But even with the glare reduced, the planet itself has to be visible. And planets don't produce their own visible light. They only reflect the star's light, which is incredibly faint.
Which is why Balmer's team wasn't looking for reflected visible light at all.
Oh, they weren't.
No. They designed their observation program around a very specific target profile. 29 Cygni b was just the first of 4 distinct objects they selected for this.
Okay, what were the criteria?
To make the cut, the objects had to weigh between 1 and 15 Jupiter masses. They had to orbit within roughly 9 billion miles of their host stars. And most critically, they had to be astronomically young.
Let's unpack the age requirement. We're dealing with objects that have temperatures ranging from about 1,000 to 1,900 degrees Fahrenheit, which is roughly 530 to 1,000 degrees Celsius.
Extremely hot.
Why is a scorching hot temperature required to see them? If the coronagraph is blocking the star, why does the planet need to be practically on fire?
Because that extreme temperature allows the James Webb Space Telescope to bypass the reliance on reflected light entirely.
Wait, so that heat isn't from the star?
No, that heat isn't generated by the host star warming the planet. The distance is far too great for that. That 1900-degree temperature is the literal residual friction and gravitational energy left over from the planet's violent birth.
The energy of assembly.
Exactly. Think about the sheer kinetic energy of billions of trillions of tons of rock, ice, and gas crashing together, compressing under their own immense gravity.
That's a lot of friction.
It is. That gravitational potential energy is converted directly into thermal energy. This is governed by something called the Kelvin-Helmholtz mechanism.
Right.
As a giant planet forms, it is initially incredibly puffed up and searingly hot. Over millions of years, it slowly shrinks and radiates that primordial heat out into the void of space.
So it is glowing like an ember pulled fresh from a fire.
And that is the secret to direct imaging. Any object with a temperature emits electromagnetic radiation, a concept known as blackbody radiation.
Okay.
For an object between 1,000 and 1,900 degrees Fahrenheit, the peak of that radiation doesn't fall in the visible spectrum that human eyes can see.
Where does it fall?
According to Wien's displacement law, the peak emission shifts into the infrared spectrum.
Which is exactly what the James Webb Space Telescope was engineered to see.
Precisely. The host star is incredibly bright in visible light, but much less dominant in the specific infrared bands where the planet is actively glowing.
Oh, that's clever.
By using NIRCam to look in the infrared and using the coronagraph to block the star, the contrast ratio shifts from an impossible 1,000,000,000 to a manageable few thousand to 1.
So they aren't looking for a firefly reflecting a searchlight. They're using thermal goggles to spot a massive glowing heat source in the dark.
A perfect way to put it.
Now, this specific temperature range, this 1900-degree heat, wasn't just useful for visibility, though. The researchers noted that this specific thermal profile placed 29 Cygni b in a very similar atmospheric state to other well-studied planetary systems.
That was a very deliberate choice on their part.
Right. The team had previously analyzed a famous system called HR 8799, which has multiple directly imaged planets. By targeting an object with a similar temperature, they could ensure the atmospheric chemistry was behaving in predictable ways, allowing them to compare their findings accurately.
That is a crucial point of scientific rigor. Temperature radically dictates atmospheric chemistry. It determines whether certain molecules exist as gases, liquids, or are locked up in solid clouds deep in the atmosphere. By keeping the thermal baseline consistent with prior studies, they isolated the variables.
So Webb successfully navigates the glare. It captures the infrared photons emitted by the residual heat of 29 Cygni b. They have the image, a glowing dot on a dark background.
A beautiful glowing dot.
But a picture alone doesn't solve the physical mystery. A glowing dot doesn't tell you if it gathered pebbles or if the sky collapsed on it.
No, it does not.
The actual answer was encoded within the specific architecture of that infrared light.
Capturing the light is merely the gathering of evidence. The actual interrogation of that evidence is the science of spectroscopy.
Right, reading the light.
Exactly. When the intense heat from the planet's deep interior radiates outward, it doesn't just travel freely into space. It must first pass through the planet's own thick, swirling atmosphere.
And that atmosphere acts as a filter.
An incredibly complex chemical filter.
How exactly does a gas filter light? Are we talking about the gases physically blocking the photons?
In a quantum mechanical sense, yes. Every molecule in the universe, whether it's water, methane, or carbon dioxide, has a very specific internal structure.
Okay.
The atoms in a molecule are bound together, and those bonds can vibrate, stretch, and rotate. But they can only do so at very precise, discrete energy levels.
So they're picky about their energy.
Very picky. When a photon of infrared light hits a molecule, if that photon's specific energy, its exact wavelength, perfectly matches the energy required to make that molecule vibrate, the molecule will absorb the photon.
The photon is literally consumed to power the vibration of the gas.
Exactly. But if the photon's energy doesn't match perfectly, it passes right through unobstructed.
Okay, I followed.
So when the James Webb Space Telescope collects the broadband infrared light from 29 Cygni b, it passes that light through specialized filters.
And splits it up into a spectrum.
Right. The astronomers look at the resulting spectrum and they look for the missing pieces. They look for the exact wavelengths of light that never made it to the telescope because they were absorbed by the atmosphere.
Like a barcode, a chemical fingerprint left in the shadows of the light.
A perfect description. And when Balmer's team analyzed the spectral barcode of 29 Cygni b, they found profound absorption signatures.
What was missing?
Entire bands of infrared light were completely missing, absorbed by two very specific molecules, carbon dioxide and carbon monoxide.
CO2 and CO. So they found massive quantities of carbon and oxygen in the atmosphere.
Huge quantities.
Now, as we know, astronomers have that remarkably quirky habit of categorizing elements. While a chemist would define carbon and oxygen as nonmetals, astrophysics takes a much broader brush to the periodic table.
It is a bit of a historical idiosyncrasy of the field, yes.
It's always funny to me.
Well, in the context of astrophysics, the universe began with the Big Bang, which produced almost exclusively hydrogen and a little bit of helium.
Right, the light stuff.
Every single other element on the periodic table, carbon, oxygen, nitrogen, iron, silicon, was forged much later through nuclear fusion in the hearts of stars or in the explosive deaths of supernovae.
So they all have that same explosive origin story.
Because all of these heavier elements share this common forged origin, astronomers simply lump them all together under the collective term metals.
So when we talk about the metallicity of a star or a planet, we aren't talking about shiny, conductive materials.
No, not at all.
We are talking about the sheer abundance of heavy, complex elements, like the carbon and oxygen found in 29 Cygni b compared to the baseline hydrogen and helium.
Correct. And this is where the spectrum of 29 Cygni b completely shattered the ambiguity of its origin.
How so?
By measuring the depth and width of those carbon monoxide and carbon dioxide absorption lines, the researchers could calculate the total concentration of these metals in the planet's atmosphere.
And to understand the significance of that number, they had to compare it to a baseline, right?
Exactly. And the baseline is the host star itself.
Because the star and the planet formed from the exact same original molecular cloud.
Precisely. The host star's composition represents the original, unaltered recipe of the raw materials available in that specific region of space.
So what's the star made of?
The host star of 29 Cygni b has a metallicity very similar to our own Sun, mostly hydrogen and helium, with a standard sprinkling of heavier elements.
Okay, and the planet.
When the team calculated the metallicity of 29 Cygni b, they found it was massively, inexplicably enriched compared to its star.
How enriched are we talking? Give me the scale.
When they took the atmospheric concentration of these heavy elements and extrapolated it across the entire 15 Jupiter mass volume of the planet, the math revealed a staggering stockpile.
Okay.
29 Cygni b contains a total mass of heavy elements equivalent to roughly 150 Earths.
150 Earths.
Yes.
I really want to linger on the physical reality of that number. We aren't just talking about a wisp of gas.
Not at all.
We are talking about the mass equivalent of 150 solid, rocky, metallic planets, complete with silicate mantles and iron-nickel cores. 150 Earths worth of solid material, completely ground up, vaporized, and integrated into the gaseous envelope of this single giant.
It is a terrifying amount of heavy material, and it is the definitive smoking gun evidence that solves the formation mystery.
Let me make sure the logic is completely airtight here. Let's go back to the top-down fragmentation theory. The idea that a massive chunk of the disk just suddenly became unstable and collapsed under its own gravity.
Right, the star formation physics.
If that had happened, why wouldn't it have 150 Earths of metal in it? Doesn't the disk have dust in it?
The disk does have dust, but you have to consider the specific mechanism of the collapse.
Okay.
If a massive section of the disk simply suffers a gravitational collapse, it is an indiscriminate process. It aggressively sweeps up everything in that region simultaneously, the gas and the dust together.
It doesn't sort it out.
Exactly. Therefore, the resulting object will have the exact same chemical ratio, the exact same metallicity as the bulk disk itself.
And the bulk disk has the exact same metallicity as the host star,
which is very low in metals. So a sudden collapse would just trap the baseline recipe. It would result in a massive gas balloon composed almost entirely of hydrogen and helium with only a trace amount of heavy elements.
Because a top-down fragmentation process possesses no physical mechanism to separate the heavy elements from the light gas.
It cannot selectively enrich itself. It just takes whatever is there in the ratios that are there.
But the bottom-up accretion process, the slow, tedious gathering of pebbles, how does that explain this massive localized spike in carbon and oxygen?
Because core accretion is, by its very nature, a mechanism of chemical separation and concentration.
Oh, really?
Remember the timeline we discussed?
Yep.
Long before a protoplanet is massive enough to start pulling in hydrogen gas, it is orbiting through the disk, acting as a relentless gravitational vacuum cleaner.
Right, gathering pebbles.
But it is specifically vacuuming up the solid material.
The rocks, the pebbles, the ice.
Yes. And what are those rocks and ice made of? They are composed almost entirely of heavy elements: carbon, oxygen, silicates, and iron.
So it's hoarding the metals.
Exactly. As the protoplanet spends millions of years plowing through the disk, it is selectively stockpiling the metals while ignoring the gas entirely.
Building a massive core.
It is building a massively dense, incredibly metal-rich core. And as more planetesimals crash into this growing core, the sheer kinetic energy of the impacts vaporizes them, releasing those heavy elements into the planet's growing atmosphere.
So by the time the planet finally triggers runaway gas accretion and pulls in the massive hydrogen envelope, it has already hoarded an immense concentrated supply of heavy elements.
Precisely. The only physical way to achieve a metallicity that is massively higher than the host star, the only way to concentrate 150 Earths worth of heavy elements into a single object, is to spend millions of years selectively sweeping up solid debris before accumulating the bulk of the gas. The chemical fingerprint in the atmosphere definitively rules out fragmentation. 29 Cygni b was built from the bottom up.
That is just an incredibly elegant piece of deduction. They used the chemical exhaust in the atmosphere to reconstruct the mechanical history of the object.
It's beautiful science.
But in science, a paradigm-shifting claim requires an ironclad foundation. And Bulmer's team knew that atmospheric chemistry, while compelling, is only one line of evidence.
You always want corroboration.
Exactly. To definitively close the case on 29 Cygni b, they needed a second, entirely independent verification. They needed to look past the chemistry and examine the orbital mechanics.
They needed to corroborate the crime scene by looking at how the planet actually moves.
Which brings us to the work of co-author Ash Messier, a graduate student at Johns Hopkins University, and their use of the CHARA array.
An incredible facility.
CHARA stands for the Center for High Angular Resolution Astronomy, and it is located on Mount Wilson in California. Now, CHARA isn't just a big mirror pointing at the sky. It is an optical interferometer array. Explain the physics of interferometry to me, because the way it simulates a massive telescope is mind-bending.
It is one of the most demanding engineering feats in ground-based astronomy today. To track the precise orbital dynamics of 29 Cygni b, and more importantly, to measure the exact physical orientation of its host star, the team needed unprecedented angular resolution.
Meaning they needed to see things incredibly clearly.
They needed to see details so fine that no single telescope mirror on Earth is large enough to resolve them. So, CHARA uses an array of 6 separate, smaller telescopes spread out across the mountain in a Y shape.
But wait, how does having 6 separate small telescopes help if none of them are big enough on their own?
By meticulously combining the light they capture.
Okay, how?
When the light waves from the distant star system arrive at Earth, they hit the different telescopes at very slightly different times, separated by fractions of a nanosecond, depending on where the telescope is physically situated on the mountain.
Right, because of the angle of the star in the sky.
Exactly. CHARA funnels the light from all 6 telescopes through a complex vacuum tube system into a central beam combining room.
Vacuum tubes.
Yes, to prevent air turbulence from distorting the light. Here in the combining room, the light bounces off mirrors on incredibly precise motorized carts called delay lines.
What are the carts delaying?
They are constantly moving back and forth on rails to add microscopic amounts of extra travel distance to the light arriving at the closer telescopes.
To even it out.
Exactly. The goal is to ensure that the light waves from all 6 telescopes arrive at the final detector at the exact same femtosecond.
And what happens when they do?
When the wave peaks and wave troughs perfectly align, they undergo constructive interference. They combine to form an interference fringe pattern.
And that perfect alignment creates a virtual telescope.
Exactly. By combining the light in this way, CHARA achieves the angular resolution equivalent to a single, monstrous telescope whose mirror is as wide as the maximum distance between the farthest telescopes in the array.
Which is how big?
Over 330 meters across.
That's a massive mirror.
It allows them to measure the microscopic wobble and the exact physical dimensions of stars that appear as nothing more than unresolved pinpricks to almost any other observatory on the planet.
So armed with this incredible resolving power, Ash Messier and the team analyzed the system. They updated the precise orbital path of 29 Cygni b, tracking how it moves through space.
Yes.
But crucially, they also measured the host star itself. By analyzing the subtle Doppler shifts and gravity darkening across the surface of the star, they were able to determine the exact tilt of the star's rotational axis.
They figured out exactly how the star is spinning.
And when they compared the star's spin to the planet's orbit, they found the mechanical smoking gun. The alignment was perfect.
Perfect alignment.
The planet's orbital inclination is flawlessly aligned with the equatorial spin axis of the star.
This is a monumental piece of corroborating evidence.
Let's break down why.
To grasp why this alignment is so definitive, we have to return to the fundamental physics of the initial molecular cloud collapse. We have to talk about the conservation of angular momentum.
Okay, this is where I always visualize a chef tossing pizza dough.
It's a great visual.
When the chef throws the dough into the air and gives it a spin, the centripetal force causes the dough to expand and flatten out into a wide, thin disc. Everything embedded in that dough is rotating on the exact same flat plane, moving in the exact same direction.
That is a perfect, intuitive, mechanical analogy. When the original vast molecular cloud began to collapse under its own gravity to form the star, it possessed a tiny, inherent, random rotation.
Just a little spin.
Right. As the cloud shrank, the conservation of angular momentum dictated that its spin must dramatically increase. just like an ice skater pulling their arms in.
So it spins faster and faster.
The majority of the mass collapsed to the center to form the star, which continues to spin rapidly on a specific axis. But the remaining material, spinning too fast to fall inward, flattened out into the protoplanetary disk along the star's equator.
The spinning pizza dough.
Exactly. The central star's equator and the flattened protoplanetary disk share the exact same geometric plane. Therefore, if a planet forms inside that disk through the slow bottom-up accretion of pebbles and gas, it is mechanically locked to that plane.
Because it grew inside the dough.
Right. It will forever orbit the star in perfect alignment with the star's equator. We see this vividly in our own solar system, where the major planets orbit in a relatively flat, orderly plane perfectly aligned with the sun's rotation.
Okay, so if it accretes in the disk, it must be aligned. But let me play devil's advocate for a second.
Please do.
What if 29 Cygni b had formed via fragmentation? If a massive chunk of gas suddenly collapsed on its own, would it still maintain that perfect alignment? Could fragmentation mimic the pizza dough?
It is highly, highly unlikely to produce perfect alignment, and here's why. While disk fragmentation can occur in a roughly coplanar environment, the sheer violence and scale of a fragmentation collapse introduces immense chaos into the system.
So it's disruptive.
Very. If the object formed from a broader fragmentation of the larger molecular cloud rather than the disk, the resulting fragment is subject to turbulent gas dynamics, magnetic field breaking, and severe gravitational interactions with other collapsing cores.
It's a much messier birth.
Incredibly messy. Furthermore, if a massive object forms via fragmentation at extreme distances, its orbit is highly susceptible to something called the Kozai-Litoff mechanism.
What's that?
It's where gravitational interactions with distant companion stars or galactic tidal forces cause the planet's orbit to wildly tilt and become highly eccentric over time. Fragmentation tends to produce orbits that are misaligned, severely tilted, or just chaotic relative to the host star's spin.
So the perfect, flat, orderly alignment of 29 Cygni b is the ultimate mechanical hallmark of a smooth, disk-bound formation.
Precisely. When you place the evidence side by side, the conclusion is inescapable.
It really is.
You have the chemical evidence, 150 Earth's worth of concentrated heavy elements definitively proving the object spent millions of years vacuuming up solid material.
And you have the mechanical evidence from Chara.
Right. A perfectly flat, equatorially aligned orbit, proving the object formed smoothly within the physical constraints of the flattened protoplanetary disk, independent methodologies yielding the exact same physical reality.
Which brings us to the ultimate realization of this entire investigation, the redefinition of the cosmic boundary.
The textbook needs an update.
It does. With both the atmospheric chemistry and the orbital mechanics screaming core accretion, astronomers are effectively forced to rethink how massive a true planet can actually get before the laws of physics break down.
Because the historical models suggested 15 Jupiter masses was an impossible hurdle for accretion.
They really thought the disk could evaporate too quickly.
And the pebbles shouldn't gather fast enough at those extreme distances. But William Balmer's ultimate conclusion summarizes the paradigm shift perfectly.
What did he say?
Despite its massive size, despite its incredible distance, 29 Cygni b, in Balmer's own words, formed like a planet and not like a star.
It formed like a planet, not a star. It defied the computer simulations that insisted core accretion couldn't build something that massive that quickly, 1.5 billion miles out in the dark.
It did.
It stands as physical proof that the universe is far more capable and perhaps far more efficient at building giant worlds from the bottom up than our models ever gave it credit for.
And this realization is just the beginning.
The research isn't over.
Far from it. Remember, 29 Cygni b was merely the first of 4 specific targets in their James Webb observation program. They are currently analyzing the exact same kind of infrared spectroscopic data for the remaining 3 objects.
What are they hoping to find in the other 3? Just more confirmation of the same thing.
They are looking for the gradient of formation. Their goal now is to actively search for compositional differences between the lower mass planets in their sample and this absolute giant.
To see how they scale.
Exactly. By systematically comparing the chemical fingerprints, the metallicities, the carbon-to-oxygen ratios across different planetary masses, they hope to glean incredibly nuanced insights into how the core accretion mechanism scales up.
So they want to figure out why the models were wrong in the first place.
Right. Does the aerodynamic drag on pebbles work differently at 1.5 billion miles than we thought? Is the disk much denser in its outer regions than standard models predict? The upcoming data will refine the very physics of planet formation.
It is a humbling reminder that nature genuinely does not care about our neat, human-made categories.
It really doesn't.
We draw an arbitrary line on a graph and declare, core accretion stops here. Planets can only get this big. Anything beyond this must be a fragmented, failed star. And the universe responds by casually presenting us with 29 Cygni b.
It just shatters the ceiling.
It does. But this raises a profound and honestly slightly unsettling question. If a planet can reach 15 times the mass of Jupiter, gathering 150 Earths worth of heavy metals just by relentlessly sweeping up rock and ice in a disk, where is the actual physical ceiling?
That is the big question.
Is there a hard limit to this bottom-up process? Or could the galaxy be hiding even bigger, more massively incomprehensible planets that we have completely mislabeled as brown dwarfs or small stars?
That is the profound implication that has the astrophysics community buzzing right now.
Really?
Absolutely. By definitively proving that a 15 Jupiter mass object can assemble via core accretion, 29 Cygni b violently kicks the door wide open. The theoretical ceiling for planetary mass has been irrevocably raised.
There could be bigger ones out there.
As Balmer's team and others utilizing the incredible power of the James Webb Space Telescope continue to map these extreme targets, we are going to define the true physical limits of planetary architecture. It opens the very real possibility that our galactic neighborhood is heavily populated with hypermassive planets, worlds of unimaginable internal pressures and scale that we previously dismissed as entirely different classes of celestial objects.
Just because we couldn't imagine they were planets.
Exactly. Simply because we lacked the imagination to believe core accretion could build them, we may find ourselves totally recataloging the cosmos.
It is wild to consider that we might be surrounded by absolute monsters of planetary engineering hiding in plain sight just because we filed them in the wrong cosmic folder.
It's a very exciting time for astronomy.
So let's bring the journey of 29 Cygni b to a close. We started with an object sitting on the absolute razor's edge of known physics, a borderline behemoth that defied every mathematical model we threw at it.
A total puzzle.
And through an incredible synthesis of human ingenuity, using an orbital observatory to capture the infrared embers of its violent birth, deciphering the spectral shadows of carbon and oxygen to reveal its heavy metal diet, and leveraging an array of Earth-bound mirrors to perfectly track its mechanical alignment, astronomers fundamentally solved the mystery.
They took an anomaly and proved it to be the definitive champion of bottom-up planet formation.
An object carrying the dissolved, vaporized remains of 150 Earths within its atmosphere.
It is the ultimate testament to the fact that the slow, steady, seemingly humble process of gathering microscopic dust and rocks can, under the right conditions, build absolute titans.
So the next time you're standing outside in the dark, looking up at the scattered points of light in the night sky, consider this. The giant worlds out there, the massive unseen objects orbiting those distant stars, they aren't all just failed stars or the results of sudden, violent gravitational collapses.
Some of them are the ultimate extreme survivors.
Exactly. They're the undeniable champions of the exact same humble dust-gathering process that slowly, over millions of years, built the solid ground you are standing on right now. And it leaves you with this lingering thought to mull over. If a planet can grow to the staggering size of 15 Jupiters, consuming the equivalent of 150 Earths just by patiently gathering cosmic debris in the dark, what other and possibly massive universe-breaking structures might be out there, quietly hiding a very humble bottom-up origin?